Hi guys, so today we are doing May-June 2016, paper 1 2, 9701 chemistry. So let's start. Question number 1. The diagram shows the Boltzmann distribution of energies in 1 mole of a gas. The gas can take part in a reaction with an activation energy EA. Which statement correctly describes the effect of an increase in temperature? So, when the temperature increases, the Boltzmann curve basically just shifts to the right on the x-axis, and the area under the curve remains the same. Okay, I'm not very good at drawing the Boltzmann curve, but this peak just becomes flatter and a bit and moves to the right, and the area remains the same under the whole curve. But the difference of, in regards to the like this activation energy remains the same, right? But the difference is that before, only these many molecules had energy greater than or equal to the activation energy, right? But now there's a greater area to the left of the activation energy, right? Sorry, not to the left, to the right. This is right. So there's a greater area to the right of the activation energy mark on the x-axis. So that means that there are more successful collisions, right? More frequent successful collisions when the temperature increases. And so, what are the options? The peak P will be higher, that's wrong. It will be lower. See, it shifts to the right, becomes a bit flatter. Peak P will be lower, that's right. And fewer molecules will have energy greater than activation energy, that's wrong. Because more molecules will have energy greater than activation energy, right? Because this area is greater now. But the whole area of the curve is still the same, but the area to the right of the activation energy mark on the x-axis is greater, basically. So then the answer is going to be A. Sorry, number D. It's going to be D, right? So yeah, hope that makes sense. Question number 2. 4 electronic configurations are shown below. 3 of these configurations belong to atoms of the elements chlorine, sodium, and vanadium. Which electronic configuration belongs to an atom of another element? Okay, so the first one is 1s2, 2s2, 2p6, 3s1, right? So 3s1, that's going to be sodium, because sodium, it's in group 1, and then 1, 2, 3, this is period 3. So if, this is the S block, right? So in period 3 and group 1, that means its electronic configuration is going to end in 3s1, basically, right? So that has to be sodium. Then this next one is 1s2, 2s2, 2p6, 3s2, 3p5. 1, 2, 3. So 3p, 1, 2, 3, 4, 5. That's chlorine, definitely, right? Because it's in period 3 and group 7. So this is the P block. So it ends like it has 3s2 and then 3p5. So it's chlorine. So this is chlorine. 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. So 3d3, right? So 4s2 and then 3d3. So 1, 2, 3, 4, 4s2. And then the D block starts from 3d, right? Um, so then this is 3d1, 3d2, 3d3. So 3d3 is going to be vanadium, right? So this is basically vanadium, and they asked about chlorine, sodium, and vanadium. So if it's not chlorine, or like this one is chlorine, sodium, this one is chlorine, this is vanadium, then this one must be something else, right? 3d6, 4s2, 3d6. So then 4s2, and then 1, 2, 3, 4, 5, 6. So probably the last one is iron. Even though they didn't ask it, they just asked which one is not sodium, chlorine, or vanadium. But basically, the answer is just going to be D, right? And yeah, the next question now. Elements X and Y are in the same group of the periodic table. The table shows the first 6 ionization energies of X and Y in kilojoules per mole. What could be the identities of X and Y? So let's check the values: 800, 1600, 2400, 4300, 5400, and then 10,400. So a big jump from the sixth ionization energy, right? And even in Y, there's a big jump from 6,000 to 12,300. So that means that X and Y must be in group 5 of the periodic table. Because there's a large jump between the fifth and sixth ionization energies, which means that the sixth electron was actually lost from an inner shell, right? So these first five electrons were lost from the valence shell, but then the sixth one was lost from an inner shell, right? And then if we, again analyze the values, then 800 is smaller than 1000, 1600 is smaller than 1800, 2400 is smaller than 2700, and so on, right? Which means basically that the ionization energy of X is always less than the ionization energy of Y in general, right? Which means that Y must be above X in the like in group 5, right? So this is group 5, Y is above X. And why is that? Because ionization energy decreases down a group, right? So ionization energy decreases down a group because the number of shells increases down a group. So even the proton number is increasing, the more dominant effect is that because the number of shells is increasing, the shielding effect is increasing, and the atomic radius is increasing as well. So the nuclear force of attraction on the valence electrons decreases. So because of the increase in the number of shells down a group. And because of that, basically the ionization energy decreases because it's easier for because the nuclear force of attraction has decreased. So the ionization energy decreases because it's easier to lose the valence electrons now due to the increase in number of shells. So yeah, it's easier to lose it, so less energy is required for ionization, and basically IE decreases anyways. So now we're going to look at the first option. So they're saying Y, because I'm looking at Y first because it's above X, right? In the group. So if they're saying arsenic and then antimony, let's check the periodic table. So this is group 5, and then you have arsenic and antimony, right? So that matches, like this could be Y and this could be X. It definitely works, but that means B is obviously wrong. But A could definitely be a correct choice. Now, next we're saying Y could be tellurium and X could be selenium. Well, tellurium and selenium are not in group 5 either, they're in group 6. So that means that we can immediately cancel out option C and D as well because we already established that X and Y are in group 5, right? So that means the answer must be A. Alright, next question, question number 4. In China, the concentration of blood glucose C6H12O6 is measured in millimoles per liter. In Pakistan, the concentration of blood glucose is measured in milligrams per deciliter. Okay, interesting. The unit liter is the unit L is a liter, 1 dm cube. The unit DL is a deciliter, zero point 0.1 dm cube. So a blood glucose concentration of 18.5 millimoles per liter indicates a health problem. What is 18.5 millimoles per liter converted to milligrams per deciliter? Okay, so what can we do? They said that the unit DL is a deciliter. Okay, so 1 deciliter is zero point 0.1 dm cube, right? According to this statement, the deciliter is zero point 0.1 cubic deciliters. Then they said that the unit L is a liter, which is 1 cubic decimeter. So if 1 cubic decimeter equals to 1 liter, right? Then how many deciliters does 1 cubic decimeter equal to? Like basically, 1 liter equals to how many deciliters? So 1 liter equals to 1 dm cube, okay? And then how many, let me just take it as x deciliters. And whatever the value of x is, that's how many deciliters there are in a liter. Actually, you can also just think of it as deci means 10, right? So if 1 liter just has 10 deciliters, then I guess. So yeah, you could think of it as that. Just like how 1 meter has 100 centimeters, because centi means 100. Similarly, deci means 10. So 1 liter has 10 deciliters. What you could do it this way as well using this information, and you could just cross multiply. So x equals 1 over zero point 0.1, which is 10 deciliters. So basically, 1 liter equals to 10 deciliters. Okay, that's just the conversion from liters to deciliters because they give you liter over here and deciliter over here, right? So now let's start the conversion. I'm going to use a different color. Okay, so let me write down what the value is, 18.5. So 18.5 millimoles per liter. And then multiply, we want to convert liters to deciliter, right? So we can multiply by liter on the top and then by deciliter on the bottom to get deciliter here. So this cancels out with this, right? That's a way to convert units. You use this method, okay? And then you want to convert from moles to grams, right? So let me put moles in the denominator so that this cancels out with this, and then grams in the numerator, okay? So now we already know that 1 liter is 10 deciliters, so we write 1 here and 10 down here, okay? Now how to convert from moles to grams? So basically gram per mole is the unit for molar mass, right? So if we just find out what the molar mass is for C6H12O6, then we can write that here. So 1 mole has how many grams, right? The unit for MR is grams per mole molar mass. So let me just find out what the MR of glucose is. So 12.0, which is the relative atomic mass of carbon into 6 percent of the mass. So then we just plus 1.00 for hydrogen times 12 plus 16.0 for oxygen times 6, right? So what does that come out to be? That is 180. Okay, so I will write 180 on top. So 1 mole has 180 grams. 1 mole of glucose with 180 grams, and then I'm just going to erase this. So now we've already converted everything. So you have milligrams per deciliter. Okay, so we've converted it. So now we just have to do this calculation, 18.5 times 180, and then divide that by 10. So you get 333 milligrams per deciliter. Okay, and is that an option? That is an option. Great. So the answer is going to be C. Okay. Next question. But I need some space. So I'm going to erase this. Each of the four species in this question are isolated and gaseous. Which species is species or species? I don't know. Which species is not planar? Okay, BF3. Let's start with BF. F. Okay, that's BF3. And boron has 3 electrons in its valence shell. So it has no lone pairs basically. And how many sigma bonds? There are 3 sigma bonds, right, to boron. So that means that the steric number, which is the total number of lone pairs plus sigma bonds for the central atom or the atom we're trying to find the bond angle with, basically this bond angle, right? FBF. So the steric number is just going to be 3 because there are 3 sigma bonds, right? And no lone pairs. So that means that the bond angle is going to be 120 degrees because it's sp2 hybridization, and that because there are no lone pairs, so it just remains 120 degrees. It's going to be trigonal planar in shape, right? So BF3 basically is a planar molecule, as the name suggests, trigonal planar. So yeah, all the molecules are in the same, not all the molecules, I mean all the atoms are in the same plane for BF3. And then we have CH3 plus. Let's draw it out. CH, H, H, and then we have plus. By the plus, we can assume that carbon has lost 1 electron, so that's why there's a plus charge on the molecule. All right, kind of like how in organic chemistry you have the carbocations or this thing, right? Kind of like that. Anyways, so carbon has 1, 2, 3 sigma bonds with hydrogen, so there are 3 sigma bonds and no lone pairs, which means again it's going to be sp2 hybridization and bond angle of 120 degrees, and again it's going to be a trigonal planar molecule. Okay, and then we're going to see C2H4, C, C, H, 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 H. Okay, so you have 1, 2, 3 sigma bonds. You could consider either of the carbons with a symmetrical molecule. So 1, 2, 3, and this is a pi bond, right? So if you have a double bond, there's 1 sigma bond, 1 pi bond. If you have a triple bond, there's 1 sigma bond, 2 pi bonds, and if you have a single bond, then it's just a sigma bond, right? So carbon has no lone pairs because carbon has 4 atoms in its valence shell, so all of them are used in bonding here, right? And there are 3 sigma bonds, no lone pairs, so that means the steric number is 3 again, which means sp2 hybridization. And again, the bond angle is 120 degrees, and it's a trigonal planar molecule. So again, this is planar. And if you check this carbon out, it's the same thing because again, it's symmetrical, right? And just a two carbon molecule. Anyways, NH3 now, ammonia. So obviously now, because these three are planar, probably you can guess that NH3 is, well, not planar. But you could also know that from like things you've studied about planar. I mean, this is not the proper way to draw NH3. It's actually, like something like this, I suppose. I'm not the best at drawing molecules, perhaps, but anyways, I'm just drawing it like this right now to simplify. It's not paper two, is it? So, one, two, three. It has five electrons in its valence shell. I'm talking about nitrogen, and there's a lone pair and three sigma bonds, right? So since there's three sigma bonds and one lone pair, that's going to give you a steric number of 4, which means that the bond angle is 109.5 degrees. But due to the lone pair, like each lone pair reduces the bond angle by approximately 2.5 degrees. So now the new bond angle will actually be 107 degrees approximately. So that means that the shape is not going to be tetrahedral. For 109.5 degrees, it's tetrahedral, but because it's 107 degrees, it's going to be pyramidal. Okay, so that's the shape of NH3, and it's not basically because it's pyramidal, right? It's not planar, right? Just how I showed you how the molecule is actually drawn. Yes, this actually represents not, but that's not right. Actually, should be like this. And that's this represents that the molecules are not all in the same plane. So yeah, they're not the molecules. Why do I keep saying molecules? I mean the atoms, like N, H, H, H. Not all of these are in the same plane. Whereas, for example, in BF3, all the atoms B and all the three fluorine atoms are all in the same plane. Like imagine a sheet of paper, so they all lie flat on the paper, basically. The molecule lies flat on the paper because all the atoms are in the same plane. Okay. Next question, anyways. Argon is a gas used to fill electric light bulbs. Under which conditions of pressure and temperature will argon behave most like an ideal gas? So, one of the assumptions of an ideal gas is that the volume of, all the individual particles is negligible compared to the total volume of the whole gas, in the container or whatever, or you could say in the closed system. Okay, so the volume of the individual particles is negligible compared to the total volume of the gas. So, under which conditions will argon behave most like an ideal gas? Well, we know from Charles' law that volume is directly proportional to temperature, right, at constant pressure. So what we can say is that, because we're talking about pressure and temperature, right? So if we increase the temperature, then the volume would also increase, right? So, and if the volume of the whole gas increases, that means that the volume of each individual particle is now more and more negligible, right? So it's behaving more like an ideal gas now, right? So I will say that high temperature makes the gas behave more like an ideal gas. And then from Boyle's law, we know that volume and pressure are inversely proportional to each other. So basically, if I decrease the pressure, then the volume will increase. Or if I basically half the pressure, then the volume will double at constant temperature. So basically, if my pressure is low, then my volume will be high, and if the volume of my gas is greater, the total volume of my gas, then the volume of the individual particles will be more and more negligible, so it behaves more and more like an ideal gas, right? So that's why gases behave more like an ideal gas at higher temperatures and at lower pressures. So the answer is going to be C, right? Because you have two ticks there. Question number 7. 0.10 grams of the volatile liquid X formed 0.025 cubic decimeters of vapor at 100 degrees Celsius and atmospheric pressure. 1 mole of vapor occupies 22.4 cubic decimeter at 0 degrees Celsius and atmospheric pressure. What is the relative molecular mass of X? Okay. So 100 degrees Celsius, I just like to convert things to Kelvin. So we'll just make it 100 plus 273. That is going to be 373 kelvins, right? And then 0 degrees Celsius will just be 273 kelvins, right? So we can use PV equals nRT, I guess, because they're both at atmospheric pressure. What we can do is we can make it P equals to nRT over V. And what we can do then is equate P1 to P2, right? So this is also at atmospheric pressure and this is also at atmospheric pressure. So let me just do that. Okay, so P1 equals P2. And then for for liquid X, because N equals M over MR, right? So I can also rewrite this as P equals M over MR and then RT over V, right? So that's how you can also rewrite it. So over here, because we have to find the relative molecular mass of X, right? And we have the mass of it. We don't have the MR. So I'm just going for P1 I'm going to take like all this information about X. So P1, the mass is going to be 0.10 grams. Then R is 8.31. And then temperature is 373 kelvins. And then, I don't know the MR. I'm just going to keep it as MR. Okay, and then volume is 0.025. Now, you could write 0.025 into 10 to the power of minus 3 to convert it into meters cube, but the thing is that I'll show you, like, it just cancels out basically. Even R also cancels out because it's the same on both sides, right? Because this is actually a ratio, right? So because basically P1 over P2 equals 1, so it's a ratio, so they cancel out, so you don't need to worry about writing the value of R or about changing dm cube to meter cube, but you do need to change the temperature from Celsius to Kelvin, because over here you're multiplying something, right? So let me just write down the things for P2 and then I'll tell you what I'm trying to say. So 1 mole and then R is 8.31 and then T is 273, right? This information. And then divided by the volume. So 1 mole and then RT and then volume is 22.4 as they mentioned. So again, if I convert it into meters cube, so the thing is that this will cancel out with this, right? But and again 8.3 when cancels out with 8.31. But for the temperature, it's different because it's 100 plus 273. You're not multiplying something, you're adding something, and basically if you try to do the calculation when it is not converted to Kelvin, then you'll get a wrong answer. You could try that, okay? So they're not actually asking for the numerical value, they're just asking about how to calculate it, I suppose. Then you just cross multiply. Okay, I hope it's not too messy and you can understand what I'm trying to do because it seems a bit messy. But anyways, 0.10 into 373 into 22.4 equals to 273 into 0.025 into MR. And I can shift that to the denominator, right? So 0.10 into 373 into 22.4 over 273 into 0.025. So this is the calculation that I have to do, and which answer does it match with? It does not match with A or B. We have 0.025 in the numerator, and then we have to have 0.10. So this part matches, but this one has 273, this one has 373. We should have 373, right? So C is going to be wrong as well, and D is going to be the answer then, right? 0.10 into 373 into 2.4 over 273 into 0.025, which gives you something. What's the answer? 122.4 according to my calculator. So yeah, that seems to be the answer. And then we're going to go to the next question. Question number 8. The equation for the complete combustion of propane 1-ol is shown. Standard enthalpy changes of formation are given. What is the standard enthalpy change of combustion of propane 1-ol in kilojoules per mole? Okay. So what I can do is I can write down the elements at the bottom. So oxygen gas and H2 gas. Okay. And then you have 3 carbon, 3C. And then how many atoms of oxygen? You have 3 to the 6 plus 4, 10. Then it's O2, right? So 10 by 2 is 5. So 5 into 2 is 5 O2. H2, you have 4 H2. So 4 H2. Right? And then, because they gave you the enthalpy of formation, so I'll make arrows upwards. Basically, we're forming CH3, CH2, CH2OH from its elements, stuff like that, okay? And 3CO2 and 4H2O likewise. So, oxygen, you don't really have an enthalpy formation because you can't really, I mean, what would it mean for oxygen to form oxygen? I mean, that's just weird, like, right? Like, it's already oxygen gas, and you have oxygen gas already, so, like, its enthalpy formation is basically zero, right? Like there's no enthalpy change. So anyways, what's the enthalpy change of formation of CH2, 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 OH? It's minus 303, so I'm going to write minus 303 over here. It's just one mole form, so no need to multiply or anything. Then for CO2, it's minus 394, but you multiply it by 3 because 3 moles of CO2 are formed, carbon dioxide. So yeah, and then H2O, it's minus 286, but because there are 4 moles of H2O formed, so I will multiply this by 4. Then I need to find this enthalpy change, right? So I'm going to keep it as X. Okay, I'll just write X over here. So this is route 1. And then you have to have the same start and the same end for both routes, right? So this is going to be route 2. Hess cycles are so cool. Hess cycles, whatever they call, okay? So yeah, now let's equate the two routes. Route 1 equals to route 2. So X, this one, equals to, now over here I'm going against the direction of the arrow, right? So I'm going to make it minus 303, okay? Then here I'm going with the direction of the arrow, so I'll just keep it as plus. You don't need to change the sign. So minus 394 into 3, then plus minus 286 into 4. Again, I don't know why they're not calculating things out in this question better than the previous question, but yeah, so they just want how to find it rather than the actual numerical answer, I suppose. Anyways, so minus minus becomes plus, right? So basically, you have to look for a plus 303 in the options. This has minus, this has plus, this has minus, this has plus. So that means because these two are minus 303, right? We got plus 303. So that means we can already, like, we can immediately eliminate options A and C because they have minus 303. Then between B and D, we have to look at the other things. So this one has minus 394 into 3, and this one is minus 286 into 4. So minus 286 into 4, minus 394 into 3. So B seems to be the correct answer. If you look at B, it's plus 3 into 394 plus 4 into 286. That's wrong according to what I got over here through the Hess cycle. So that means that D is going to be wrong as well. Therefore, the answer is going to be B. Okay. If you want to calculate out the answer, 303 minus 394 into 3 minus 286 into 4, it gives you minus 2023 kilojoules per mole, I think. So, next question. In the treatment of domestic water supplies, chlorine is added to the water to form HClO, Cl2 aqueous plus H2O liquid gives H plus aqueous plus Cl minus aqueous plus HClO aqueous. The HClO reacts further to give ClO minus ions, and HClO aqueous plus H2O liquid yields H3O plus aqueous plus ClO minus aqueous. Okay, so both HClO and ClO minus kill bacteria by oxidation. That's cool. What is the oxidation? What is the change in oxidation number of chlorine when forming the ClO minus ion from aqueous chlorine? So you're forming the ClO minus ion, this one, from aqueous chlorine, which is this species, right? So the change in the oxidation number of chlorine from here to here. So Cl2, it's how chlorine exists naturally. I mean, obviously it doesn't exist in like aqueous form, it exists as a gas, but it exists as Cl2, right? So I'm going to take that as 0. That's the oxidation state of the Cl2, the elemental form, like how it exists elementally. I suppose that more. Anyways, Cl minus aqueous, oxygen has a fixed oxidation state of -2. Usually, there are a few exceptions like OF2, and I don't remember all of them, but maybe it was H2O2 as well, perhaps. It was H2O2, yeah, perhaps. And yeah, it was H2O2. H plus be plus 1 times 2, and then O2 would be plus 2x, we don't know it, so that equals to 0, whole compound is 0, so 2x equals -2, and x equals -1. So here oxygen has -1 oxidation state. And anyways, I'll start going into more tangents, but better if I do this calculation. So oxygen here is -2, it has an oxidation state of -2, chlorine we don't know, so we're going to take it as x, and then the whole ion has an oxidation state of -1. Oxidation number. So then what is x going to be? It's going to be -1 plus 2, so it's going to be +1. So basically over here chlorine has an oxidation number of +1. And so what's the change? The change is from 0 to +1, which is +1 obviously. So the answer is going to be C, right? Yeah. Next question. When solid ammonium chloride dissociates at a certain temperature in a 0.500 cubic decimeters container, so it's not 1 cubic decimeter, it's 0.500 cubic decimeters, be careful about that. Container, okay, so then what happens? Ammonia and hydrogen chloride are formed, that's cool. The initial amount of ammonium chloride was 1.00 moles, and when the system had reached equilibrium, there was 0.300 moles of ammonium chloride. What is the numerical value of Kc for this reaction under these conditions? Okay, so we will make an ice table, right? So this I stands for initial, C is change, then E is equilibrium. So that's what an ice table is. So initial moles basically, and change in moles, and then equilibrium, the mole number of moles at equilibrium. So this is 1.00, this is 0, and this is 0 initially, right? And then the ammonium chloride will dissociate. Eventually, it will reach equilibrium. So then at equilibrium, there's 0.300 moles of ammonium chloride, so this is 0.300. And then we will see what the change is. So 1.00 minus 0.30 is going to be a change of minus 0.700, right? It decreased by 0.700. So because this is a 1:1:1 molar ratio, all of it. So if this, NH4Cl decreased by 0.700 moles, then NH3 will increase by 0.700 moles, and so will HCl, right? HCl will also increase by 0.700 moles. So this is also 0.700, and this is also 0.700. But take note that for Kc, we don't only consider moles, you have to take the concentration, right? So case, like not Kc actually, let me just write concentration, okay? Concentration and equilibrium. So actually, this is a solid, and these two are gases, note that. So for the gases, it's simple. It's just going to be 0.700 divided by 0.500, right? So concentration equals moles per unit volume. So it's zero point 0.7 divided by the volume of the container. So then that is going to be 1.40, right? And even this one is the same value, so this is also going to be 1.40. But because ammonium chloride is a solid, so its concentration, well, I mean, solids are considered really not to have a concentration, or you could say that basically they have a concentration of 1 unity. This is called unity. One is called unity. Okay, so basically, their their concentration does not affect the value of Kc so much. Like, I mean, they just have a concentration of 1. You just assume them to have a concentration of 1. Okay, so Kc equals to NH3 HCl basically, or you could also write down NH4Cl in the bottom, and then what you do is when you're calculating Kc, you just replace the value of NH4Cl by 1 because it's a solid, right? So it doesn't, 1 will not affect the value basically. And then NH3, its concentration is 1.40, and HCl is also 1.40, so 1.40 times 1.40, or you could say 1.40 squared. So that is going to be 1.96 mole square dm minus 6. So how do you get that? You get that mole per dm cubed, and you just square that. So yeah, mole square dm. Okay. So yeah. And then is there an option? That is an option, so that's option C. So we're going to select that. Okay, next question. Which stage in the free radical substitution of ethane by chlorine has the lowest activation energy? Okay, lowest activation energy. So it is like it occurs the most easily, it requires the least energy to occur. So it's most spontaneous, I suppose. So this is the initiation step, because this is the molecule and you're getting two free radicals from that, right? And so there's only bond breaking here, right? There's no bond formation. So it's only bond breaking, which means that it's an entirely endothermic process, which requires energy, right? And it requires a lot of energy, because that's why I would assume that it has a high activation energy. And you do know that, like, when we're doing free radical substitution of ethane by chlorine, we need UV light for that, right? Like sunlight, UV light. So basically, the initiation step requires a high activation energy. I mean, I would assume that's why we use UV light, okay? And then these two, Cl plus CH2H6 is C2H5 radical plus HCl, and C2H5 radical plus Cl2 gives C2H5Cl plus Cl radical, okay? So these are propagation steps. Propagation. And there is bond breaking happening as well as bond formation, right? So that means that um, we can't really determine exactly whether it will be a high activation energy or low activation energy. But there is that thing that the propagation steps are chain reaction, like it's a sort of chain reaction after the initiation step. The free radical substitution is a chain reaction, right? So obviously there's less energy required than was required for the initiation step, right? But then, the termination step is actually the one that has the lowest activation energy. And why is that? It's because there are two free radicals reacting, and free radical species are highly reactive. So free radicals are highly reactive. They, because they have, one um, unpaired electron, and so they are very, very reactive because of that. Yeah, and so and again, there's only bond formation taking place here, right? So these two highly reactive free radicals are reacting together to form, like it's just bond formation, C2H5Cl, which is an exothermic process. So it will have a low activation energy because there's really no bond breaking taking place here, and they they react very readily with each other. Like these two free radicals will react very readily because they're so willing to react because they have an unpaired electron in their valence shell. Okay, so then the answer is going to be D, right? Because it's just bond formation and these two highly reactive free radicals are reacting together. So yeah, it's going to be the one with the least activation energy. Okay, then the highest activation energy would be A. Okay, now sodium and sulfur react together to form sodium sulfide Na2S. How do the atomic radius and ionic radius of sodium compare with those of sulfur? So this is period 3, right? Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, right? So we're looking at sodium and sulfur. So let's look at the periodic table here as well. Suppose I could have done that before instead of writing them all out. But anyways, sodium is here. It has a proton number of 11, and then sulfur has a proton number of 16, right? So just note that, like, in a period, the number of shells is the same, right? The number of shells remains the same across the period. Whereas down a group, the number of shells increases, right? But across a period, what's happening is that the proton number is increasing, right? From 11, 12, 13, 14, 15, 16. So sulfur has the same number of shells as sodium, but it has a greater proton number. So the shielding effect is fairly similar, but but the number of shells is the same, but the difference is that sodium, it has less protons than sulfur, and because sodium has less protons, there's going to be less nuclear force of attraction on its valence electrons than there is in sulfur. So the nuclear pull on the valence electrons is less in sodium. So that's why sodium is going to be um, slightly bigger than sulfur. Okay, and so basically what I'm trying to say is that across a period, the atomic radius decreases slightly due to the increase in the proton number, and so there's greater nuclear force of attraction in the valence electrons across a period for the same number of shells. Okay, so sodium is going to have a slightly bigger atomic radius than sulfur. And now then next they're asking about the ionic radius, right? So as for the ion, like over here, which period are sodium and sulfur in? This is period 1, period 2, period 3, right? So they're in period 3. So basically they have three shells that are occupied. Yeah. So they have three. Let me just assume that this is sodium. Okay, I'm just going to fill the outer shell. Okay? So in the outer shell, sodium has just one electron because it's in group 1, and then sulfur is in group 6, so it has 6 electrons in its outer shell, right? And then, these are very crude drawings, but anyway, what's going to happen is that sodium, it's easier for sodium to lose that electron than to gain 7 electrons, right? So it's going to lose this electron, okay? And so it just has two filled shells now. Whereas for sulfur, like it's easier for sulfur to gain 2 electrons than to lose these 6 electrons, right? So it's just going to gain 2 electrons in the same shell. So now sodium has a complete octet, like this second shell of sodium, it has 8 electrons. It lost that 1 electron in its third shell, right? and sulfur it has the third shell now completely filled. So basically, as you can see, sodium, because it has one less shell, like now it's not sodium anymore. In fact, it's Na plus, and sulfur is the sulfide S2 minus ion, right? So now, if you're talking about the ionic radius, sodium ion has one less shell than the sulfide ion, and because of that, you know, yeah, the ionic radius is smaller basically, right? So sodium is going to have a smaller ionic radius than sulfur, as you can see. Okay. So now we have two ticks at D, so I'm going to say the answer is D. Okay, yeah. Okay. All right. So solid aluminum chloride sublimes at 178 degrees Celsius. Which structure best represents the species in the vapor at this temperature? Okay. So aluminum chloride, we would assume that it's either in the form AlCl3 or Al2Cl6, right? Al2Cl6 is a very stable compound compared to AlCl3, because in AlCl3 the aluminium has an incomplete octet, right? So, so over here, like aluminium, it has three electrons. Wait, computer stuck. Wait a while. Okay. So Al in AlCl3, like aluminium has three electrons in its valence shell, right? Aluminium is in group three. So then it's how many, like it's forming sigma bonds, like three sigma bonds with chlorine just single bonds. So there's one, two, like how many electrons does aluminum have in its valence shell now? Like in total, one, two, three, four, five, six. So it is just six, which means it's an incomplete octet, right? So it's less stable. AlCl3 is the less stable form, whereas Al2Cl6 is more stable because chlorine donates one of its lone pairs to aluminium. So now aluminium has one, two, three, four, five, six, seven, eight electrons. So it has a complete octet now in Al2Cl6. So Al2Cl6 is more stable. All right, and actually, if we check, like I would think that because Al2Cl6 is more stable, I mean obviously it's not D, Al3 plus Cl minus 3, and over here aluminium is donating lone pairs to Cl, which is just weird. I don't know why you circle around that, but that's wrong, right? So I would say that it's A because it's just sublimed, right? So I would assume that it would still remain Al2Cl6 because that's the one that exists at lower temperatures and it's more stable. It's just sublimed, right? And if you increase the temperature more and more and more, then it might become LCLC. But if it's just sublimed, I would assume that it's Al2CL6. So yeah, Al. Check that. So the sublimation of the molecule depends on the molecular forces. So it sublimes at 180 degrees Celsius. Yeah, but it does exist at lower temperatures. Like it would be like if I check AlCl3 exists at low temperature, that would definitely sublime. LCN3. So L2CL6 exists at, yeah. So it's remarkably stable. Even at the sublimation temperature, which is 180 degrees Celsius, it exists at a timer at higher temperature. So my screen keeps getting stuck today. So it dissociates into the mold at higher temperatures. But even at the sublimation temperature, it's fine. Okay, so that's what I don't like about this search engine thing. It doesn't give you what you need unless you use the right words, which is annoying. Google is better. But anyway, let's continue. A 0.005 mole sample of anhydrous calcium carbonate was thermally decomposed to give 100 cubic centimeters of gas measured at a certain temperature and pressure. A separate experiment carries the same temperature and pressure. A 0.005 mole sample of anhydrous calcium nitrate was completely thermally decomposed. The volume of gaseous products was measured. What total volume of gaseous products was formed from the calcium nitrate? Because you're thermally decomposing it, so let me write that equation down first. So you have CnO3 twice, giving you CaO plus NO2 plus O2, and let's balance it now. So Ca is already balanced, and then we have to balance the nitrogen. So we have two nitrogen atoms on the left hand side. So we're gonna put a 2 here. Two twos are 4, 5, 6, 7. This is 6. So let me make this 1 by 2. That's 1 plus 4, 5, and then 6. So it's balanced now. And so we have 0.005 moles of calcium nitrate anhydrous, and then we have 100 cubic centimeters of gas. So in total, this is 100 cubic centimeters, right? And oh, they're saying it's a separate experiment, but this one was completely thoroughly decomposed to okay, volume of gaseous products measured. What total volume of anhydrous of gaseous products was produced from the oh, okay, so in the first one they're talking about calcium carb. Okay, fine. So this is we don't know this is 100 cubic centimeters. Okay, so this one they're talking about calcium carbonate. This one they're talking about calcium nitrate. So this is for this part of the question. This is the equation that we use. Okay, but for the first part, you have CaCO3 giving you CaO plus O2, and just check if it's balanced. And it is balanced. You have three oxygen on the left hand side and the right hand side. But it should be CO2, right? Because we're carbon both. Yeah. So now we have 100 cubic centimeters of gas, and that gas is completely just going to be carbon dioxide because CaO exists as solid and CaCO3 is also solid, right? So the gas is completely just carbon dioxide, right? It's 0.005 moles, right? So what can we say? So the thing is that they have said at a certain temperature and pressure, but we don't know what the temperature or pressure is now. We know that, like, how they say that 1 mole of a gas at room temperature and pressure occupies a volume of 24.0 cubic decimeters, right? But the thing is that that's at room temperature and pressure, but they said at a certain temperature and pressure, we don't really know what that certain temperature and pressure is. So the gas won't be occupying a volume of 24.0 cubic decimeter, but it will be occupying every mole of a gas, like, 1 mole of a gas will be occupying a certain volume. It's known as molar volume. So N equals V over, we usually say 24.0, but that's at room temperature. So actually, we don't know the molar volume here. So I'm just going to take it as Vm, which represents the molar volume, like the volume of 1 mole of the gas at this certain temperature and pressure, basically. And we have to find what the molar volume is. Okay, so Vm equals to V over N. And from the equation, this is a 1:1 molar ratio, right? So if there's 0.005 moles of CaCO3, there's going to be 0.005 moles of CO2, okay? So I'm going to take what's the volume? It's 100 cubic centimeters. So let me convert that to decimeters, cubic decimeters. That's going to be into 10 to the power of minus 3. And the moles are 0.005. So now we will find out what the molar volume is at this certain temperature and pressure. So it's just going to be 20. This comes out on my calculator to be 20 cubic decimeters. Okay, so at this temperature, basically we have, or at temperature and pressure, we have 1 mole of the gas occupying 20 cubic decimeters of volume. Okay, so yeah, now we know what the molar volume is, so we're going to use this relationship N equals V by 20. And for the other gases, like, because this one is carried out at the same temperature and pressure, right? That's why this is useful. And now what we're going to do is that over here we know that this is 0.005 moles. From the molar ratio we can tell that because CaO is solid, NO2 is gaseous, and then O2 is also gaseous, right? And they said that we have to find the volume of gaseous products and what's the total volume of the gaseous products, right? So we basically can find the volume of NO2 and O2 combined. So if this is 0.005 moles, oxygen will be 0.005 divided by 2. So that's going to be point, because 1 is to half, right? It's going to be 0.0025 moles, right? And then for um, NO2 is going to be 0.005 multiplied by 2, because this is 1 is to 2 molar ratio. That's going to be zero point zero 0.01 moles. Okay, now we know what the moles of nitrogen and oxygen are. Now we use this equation that we got, n equals v over 20. So that's basically n equals v over 20, means that if you want to find the volume, then it's going to be v equals 20n, right? And this is in cubic decimeters. So that's the thing actually, because they got all the answers in cubic centimeters, right? So you could do the conversion right now. Like you could make it, instead of 20, like 1 cubic decimeter has 1,000 cm cube, right? So you could make it 20,000, this is dm cube, and 20,000 n cubic centimeters. Or you could do the conversion later. I'll just do the conversion later, honestly. Okay, but you could do it like this as well. But what I'm going to do is that v equals to 20n, right? So 20 times for a nitrogen, sorry, not nitrogen, nitrogen dioxide, NO2, is going to be 20 times 0.01, and then for oxygen is going to be 20 times 0.002. Okay, I'm just using this formula, and this is going to give me my answer in cubic decimeters, 20 into 0.01, answer plus 20 into 0.025, so that is going to give me um, zero point 0.7. Did I do something wrong? Okay, I think I did. 20 times 0.0025. Okay, well, just a calculation error. Yeah, it's actually 0.25. Let me just check again. 20 into 0.01 and then answer plus 20 into 0.0025. Yeah, that one is 0.25 dm cube. So now if you want to convert it to centimeters cube, just multiply this by 1,000. Okay, so you get 250 cubic centimeters, which is option D. Okay, so that is going to be your answer. This is a cool question, honestly. I mean, it's an interesting concept. Next, this is the next question, which is question number 15. Ammonia gas NH3 and hydrogen sulfide gas H2S react together to form the salt ammonium sulfide NH4 twice S. Ammonium sulfide dissolves in water to produce an orange alkaline solution. Okay. The addition of NaOH aqueous, which is a base, to the solution produces a gas X. Okay. The addition of HCl aqueous to a separate portion of the solution produces a gas Y. What are the identities of X and Y? Okay. Suppose for, like, I mean, we have NH4 here, right? Which, I mean, you know that NH3 is basic, and then NH4 plus salt will be acidic. So if you are adding NaOH, you have OH minus, then NH4 to S has NH4 plus. So I can just say, should this be right? I suppose so. NH4 plus OH minus, gives you, like, you can do this test in the lab. So it's going to be H2O plus NH3, right? So you get NH3 gas, um, and they're saying that a gas X is produced, right? So then this must be the gas X, right? So I'm going to say that X is NH3, and then for H2S, you could think of it as you have this S2 minus. So S2 minus plus 2H plus gives you H2S gas, I suppose. So because yeah, they're saying for separate portion of the solution anyway, so it's H2S gas. So then you're going to tick this option and this option, and where do you have two ticks? You have two ticks here, so the answer is going to be C, right? I suppose you could do other equations as well. I mean, maybe you could do, like, for this one you could do SH minus plus H plus, perhaps gives you H2S. I guess you could do this question using multiple equations, maybe. I mean, again, if I'm making any mistakes, just tell me in the comments, guys. But I think the answer is C. Okay. Next, a solid T was placed in an excess of the liquid U, a colorless gas was given off, and a white precipitate was seen. The precipitate was not T. What could be the identities of T and U? Okay, so first you have BaCO3 and H2O, right? So, well, I mean, that won't really give you a reaction, right? Because group 2 carbonates are insoluble in water, right? So, I mean, actually, all carbonates are insoluble in water except group 1 carbonates and NH4, NH4 2 CO3 as well, I suppose. So, but other than that, like other than group 1 carbonates and ammonium carbonate, all group 2 all carbonates in general are insoluble. But yeah, there will be no reaction ready here. Then over here, for Ca plus dilute H2SO4, you would get um, CaSO4 plus H2. And in fact, for the one in the bottom, you would also get MgSO4 plus H2. But the difference is that um, you know, if I write down the group 2 carbonates, so you have BSO4, MgSO4, then calcium sulfate, strontium sulfate, and then barium sulfate, and then radium sulfate, if I'm not wrong. Okay, and the solubility of the sulfates decreases down the group, right? So for sulfates, the solubility decreases down the group, which means that MgSO4 is soluble in water, whereas CaSO4 is only very slightly soluble in water, very, very slightly soluble. And the ones below it, like SRSO4, BSO4, RSO4, they're like basically insoluble, right? They're insoluble. But MgSO4 is quite soluble in water. So that means basically if they're saying that a white precipitate was seen and a colorless gas was given off, so this reaction there was no reaction, right? But here you do have in both of these a colorless gas given off, but the difference is that MgSO4 will dissolve in the aqueous solution, right? In the, I mean, yeah, because it's H2SO4 aqueous solution. So, MgSO4 will dissolve, but then CaSO4, it's uh, only very slightly soluble, basically. So, um, you know, we could say that a white precipitate is seen, basically. So, B could be an answer, I guess, but let's look at the last option. And, last option you would get let me just make this 2HCl. So then, if it's SrCl3 plus 2HCl, so you'll get SrCl2 plus H2O plus CO2, right? So the thing about SrCl2 is that again it's an aqueous compound, right? So I mean to say it will dissolve. So SrCl2 will dissolve as well. So a white precipitate will not be seen, and since there is no white precipitate seen, so this is not the correct option either. And so basically the only white precipitate, see, even though you do get a colorless gas CO2, but it will SO2 will also don't get a white precipitate, and so the only possible answer then will be D, right? Because that's where you get a colorless gas and a white precipitate, which doesn't dissolve or doesn't dissolve that easily, right? So CaSO4. Okay, next question. Nitrogen 2 oxide NO, nitrogen 4 oxide NO2, carbon monoxide CO, and unburned hydrocarbons are present in the exhaust gases of internal combustion engines. When catalytic converters are used to remove these compounds from exhaust gases, redox reactions occur. What happens to each compound in a catalytic converter? So, the what's the equation of things in the catalytic converter? I mean, the main equation that you associate with the catalytic converter is 2CO plus 2NO gives N2 plus CO2, right? So that's the main equation. Is that balanced? I don't think it's balanced. Wait, let me. I just randomly put the coefficients as I remember them, but I suppose I should take a risk like that and actually see if it's balanced myself. Yeah, 1 by 2 and 2. Okay, yes, that makes more sense. So now it's balanced, right? So now over here, NO, my oxygen has a fixed state of -2 oxidation state, and N is going to have a fixed oxidation state of +2. Okay, and then in N2, because the pure elemental form, so it's going to be 0 oxidation state, and so it's going from +2 to 0, so the oxidation state is decreasing, which means that the oxidation number is decreasing, so it means it's being reduced, right? And same happens for NO2, that NO2, like oxygen has an oxidation number of -2, since there are two oxygen atoms, so 2 times -2 is -4, and overall oxidation state of a compound is 0, right? So then that means that nitrogen must be +4, because -4 will be +4 -4 will be 0. So from +4 to 0, again, it's reduction that's taking place, right, of NO2, because the oxidation number is decreasing. Whereas for CO, in CO2, this is +4. Again, using the same logic as we did for NO2, this would be -2 times 2, which is -4. So to balance that, carbon has to be +4, right? And since if that is +4, over here you have oxygen is -2, so then carbon must be +2. So from +2 to +4, it's an increase in the oxidation number, right? So if the oxidation number is increasing, that means that it is oxidation. So this is becoming oxidized. And hydrocarbons as well, like, they have the same logic, whatever you have, CXHY or whatever. But again, it will be oxidized. And honestly, that's what you do, right? Like, they will be oxidized using oxygen to give you carbon dioxide and water. So that's probably what will happen. I guess. And the point is that like CXHY2 XCO2, like you usually associate that with O2, so then that is an oxidation process. Okay, I feel like I'm just saying very random things today. I guess I shouldn't. I should stop recording videos so late because that makes me sleepy. I should record at a better time. But anyways, let's continue. Okay, the answer is C then. Reduce oxidation. It should be. And question number 18. An excess of chlorine gas, CO2, is passed through 60 cubic centimeters of cold aqueous zero point 0.1 moles per cubic decimeter sodium hydroxide. In a separate experiment, an excess of chlorine gas is passed through 60 cubic centimeters of hot aqueous zero point 0.1 moles per dm cube sodium hydroxide until no further reaction takes place. How much more sodium chloride will be produced for the reaction with hot NaOH than with cold NaOH? Okay. So let's write down the equations first. Cl2 with cold NaOH, right? So that will give you NaClO. So one of them is NaClO, and then the other one, the other chlorine atom will be NaCl, and you would have H2O. So if you balance that, then you just have Na, so 2 NaOH, and that's balanced, right? Wait, um, that seems balanced, definitely 2H, so H2O. Oh, right, it's balanced. Okay, so that's the equation for the first one. Yeah, next one, the equation would be Cl2 plus NaOH gives you NaClO3. So this is actually, I guess, a case study from AS, so you should know it. And then NaCl plus H2. And you could balance this using redox stuff as well, but because it's a case study, I already know that this is 3Cl2, 6 NaOH, 5 NaCl here. That would just be 1. And then we have 6 as an NaOH, right? So 3H2O. Or you could balance this using redox things. So 3 oxygen plus 3 oxygen gives you 6. So this is balanced, right? And then how many moles of sodium hydroxide do you have? You have, N equals CV, right? So it's 60 times 10 to the power of -3 to convert to dn cube, and 0.1 times 0.1. So that is going to be 6.00 10 to the power of -3, or you could say 0.00600 moles per dm. No, it's just moles. It's moles that we're calculating. Okay. Okay. Let me just check if I do this right. And then we have 0.00600 moles of this, and the second one also uses the same, right? 60 cubic centimeters and 0.1. So this is also going to be 0.00600 moles, right? And then we have to find how much sodium chloride is produced, right? So this is a 2:1 molar ratio between NaOH and NaCl. And over here you have a 6:5 molar ratio, right? So over here this is just going to be 0.00600 divided by 2. For NaCl, so it's going to be 0.00300 moles, right? But over here you're just going to cross multiply sort of. So x is equals to 0.00600 times 5 and then divided by 6. Okay, so you just, if you see this, like 6 NaOH, 5 NaCl, so 0.00600 moles of NaOH gives you how much NaCl, right? So just cross multiplying, and how much do you get? 0.00, yeah, 0.00500. That's the 6, this cancels 6.00500 moles, okay? So this X is basically 0.00500 moles, I guess numerical value, and then have to find out how much more sodium chloride will produce, right? Then you're just going to subtract these two values. So 0.00500 minus 0.00300 will give you 0.00200 moles, right? So that is going to be A. So A would be our answer. Okay. Next question. Fluorine and iodine are group 17 elements. Their melting points are different due to differing strengths of van der Waals forces between molecules, which row is correct. So let me just write down group 7 halogens: fluorine, chlorine, bromine, iodine, astatine. Alright. So all of these are covalent compounds. And obviously this is the molecule of F2, for example, or the molecule of I2 or whatever. Then there is no electronegativity difference between F and F, right? Or between I and I. So because of that, they are non-polar compounds, and non-polar compounds, their intermolecular forces are just uh, temporary dipole-induced dipole intermolecular forces, also known as London dispersion forces, and some other names as well. But I'll just call them London dispersion forces. Okay, so 'cause that's a cool name. Sounds funny. Okay, so the strength, or you can just say temporary dipole forces, I suppose. Or I call it that. That seems simpler to say. So the strength of the temporary dipole forces increases down the group 7 halogens. And why is that? It's because basically the number of electrons increases in the molecule, right? So obviously, down the group, the proton number increases, and because the proton number increases, like along with that, the electron number also increases, right? So down the group. So fluorine has less electrons than iodine. Iodine has more electrons than fluorine. Since it has more electrons, it will have stronger temporary dipole forces, or you could call them van der Waals forces as well. So stronger temporary dipole forces. And because it has stronger intermolecular forces, like I2 will have stronger intermolecular forces, right? Because of that, it will have a higher melting point, like because it's hard. Wait, I2 has stronger intermolecular forces, right? And so basically, first let me just put things, okay? So I2 has stronger. This is the opposite. Strength of van der Waals forces. I Wait, why did they put the arrows upside down? Whatever. Then I'm looking at I2. I2 is greater than F2. And over here, I2 is greater than F2 as well. I2 is greater than F2. So I was looking at it the opposite way, sorry. So yeah, I was right according to me at least, I don't know. But yeah, I2 has stronger intermolecular forces than F2, so that means that this will be cancelled. Sometimes, even though like no matter how much math you've done, you just get confused by the greater than and less than sign. It's just, I always remember that one of my teachers used to say it's an alligator. I mean, whatever, but I cancel that out. So it's I2 has greater intermolecular forces than F2. I2 has greater molecular. So basically, B or C could be the right answer. And then if you look at the other thing, so because I2 has greater intermolecular forces than stronger intermolecular forces than fluorine, stronger temporary dipole induced dipole forces, so it's going to have a greater melting point. Like it's harder. It takes more energy to melt I2 because of the stronger forces of attraction between its molecules, right? So again, it could be I2 is greater than F2, I2 is greater than F2, okay? So that is going to be the answer we have, where we have two ticks. We have two ticks on C. So then C is going to be the answer. Next question. Chlorofluorocarbons damage the ozone layer by undergoing reactions with the free radical mechanism. The first stage of this is initiation. Which equation is most likely to be the initiation stage when chlorofluoromethane is involved in such a reaction? Okay, so if you look at all of them here, you have it's initiation, right? So initiation should get two free radicals, which is the case in all of these. But oh, this one has three free radicals, and they said most likely. Then this would probably not be most likely, would it? I mean, would most likely in the initiation step you get two free radicals, and I guess so you can cancel that out. Over here you have three free radicals, but two free radicals, sorry. And the thing is that over here you have a hydrogen free radical, which is wrong. And why is it wrong? Because you usually never really get a hydrogen free radical as an isolated product in free radical substitution. So this is like very, very, very unlikely, like getting a hydrogen free radical like this, you know. And then the choices between fluorine and chlorine. Now this comes down to the bond strength of CF versus the bond strength of CCl, right? So if we write down the group 17, like sort of CF, then you have fluorine, then you have chlorine, then you have bromine, then you have iodine, then you have acetylene, and people always forget about acetylene, poor acetylene. Okay, anyways, so we're comparing CF and CCl, right? So CCl, basically the chlorine atom has one more shell than the fluorine atom, right? So because it has one more shell, so it means that it has a longer bond length. So CCl bond is longer in length, right? And because of that, the CCl bond is weaker than the CF bond. And since the CCl bond is weaker, it takes less energy to break the CCl bond than it does to break the CF bond. So basically, CCl bond has a lower bond enthalpy, right? And because of that, the CCl bond, because it's easier to break, so CCl bond is likely to be broken first, or likely to, because it's the most, like, it's the easiest to be broken, so it's the most likely to be the first step, the initiation step, because obviously the more favorable reaction will take place first, right? So then the answer is going to be B. Okay, next question. Synthetic resins can be made by polymerization of a variety of polymers, including prop-2-ene 1-ol, CH2 double bond CH CH2OH, which structure represents the repeat unit in poly prop-2-ene 1-ol. So let's just draw out this molecule in this form, displayed form. All right. Free display. Okay, so not free display. Display this part, but anyways, now what we're going to do is to make the addition polymer. What we have to do is first we have to break this, the pi bond. So it's just like this, and then we're going to keep these bonds. No, there's just a single bond between this the C and the C, right? So this is just going to be like this, and then we're going to add, side bonds, connecting bonds, and then it's just however many units of monomers you have. So you just write that here. So N of this monomer, and then you have that monomer chain. This repeat unit repeated n times. So anyways, which structure matches with what I drew? First one doesn't match. Second one, does it match? It does match. Okay. Kind of the double bond still, which is wrong. And this one again doesn't match. So the repeat unit is represented by B, right? It's exactly what is the same as this one. So yeah, it's B. Next question. Oct-1-ene CH3 CH2 5 CH double bond CH2 can be thermally cracked. Which combination of compounds W, X, Y, and Z can be obtained by thermally cracking oct-1-ene? So basically, oct-1-ene has 8 carbon atoms, right? 1, 2, plus 5, 7, and 8. Yeah, it has 8 carbon atoms. So As long as the carbon chain is shorter than that, the product should be possible. So this one has two carbon atoms, this one has three carbon atoms, and as long as it's a valid hydrocarbon, I suppose. So one, two, three, three carbon atoms. This one, two, three, four, four carbon atoms. So all of these are possible really. So it's not B, C, or D. It has to be A because you have a bucket of octane or whatever. It's not just one molecule that we're talking about. So you could have any possible um, combination of smaller compounds, smaller hydrocarbons, as long as they're an alkene or alkane or whatever. But yeah, as long as they're an alkene or alkane, right, and shorter than 8 carbon atoms, basically, smaller chain. So 2, 3, 3, 4, these are all valid. Okay, next, a cycloalkene with the molecular formula C7H12 was oxidized by hot concentrated acidified MnO4 minus. The only organic product was 2-methylhexane 1,6-dioic acid. What is the identity of the cyclohexane? So hot concentrated acidified MnO4 minus. So this alkene bond will be completely ruptured, right? So it is, I don't know what it's called, murdered. It's called oxidative cleavage or rupturing of the um, bond, the CC double bond. And so because this is a primary carbon, this is also a primary carbon, so you will get a COOH here, right? So you'll get what do you call it? Carboxylic acid group here, okay, and also on this side. Then here again, where this one is a secondary carbon because it has 2 carbon atoms attached to it, right? This carbon, just two other carbon adjacent carbon atoms. So this one will become a ketone when it's oxidized. So let me make this molecule, and this side will become a carboxylic acid again because it's a primary carbon, and this is how it is. So this one will become, again, this is a primary carbon, this is a primary carbon, so both sides will get carboxylic acid. Wait. It's so hard to draw. Rings, okay. This is, yeah, okay. So then it's going to be like this and like that. Okay. And this is going to be, well, this side you have a primary carbon, this side you have a secondary carbon because this carbon atom, one that I highlighted in yellow, it's attached to two other carbon atoms, right? So it's a secondary carbon. So then this one, I will draw it like this. It's just going to be a ketone here, okay? And CH3. And on this side, it's going to be a carboxylic acid group, okay? So that's all 4 molecules around. Now I need 2-methylhexane 1,6-dioic acid. So the main chain has to be 6 carbon atoms long, I suppose, because it says hexane. And let me just see which one has 6 carbon atoms. So 1, 2, 3, 4, 5, 6. Okay, this has 6 carbon atoms, so it's hexane definitely. And dioic acid, yes, because on the first and sixth one it has a carboxylic acid group, which is right. And then it has to have a branch 2-methyl on the second carbon atom. So 1, 2. Yep, that's all valid. So I would say that A is the answer then because it satisfies all the conditions. This one, where does it start? So it starts from here, right? So this is the first carbon atom. Or you could actually start counting from here. So this is the first carbon atom. Second, third, fourth, fifth, sixth, seventh. So it seems to have 7 carbon atom chain, which I guess would make it invalid if I'm not counting wrong or anything. B would be wrong. Then this one seems like a dioic acid, but then 1, 2, 3. So it has the branch on the third carbon atom, right? So 1, 2, 3, 4, 5, 6. Like it's a hexane 1,6 dioic acid, but it's 3-methylhexane 1,6 dioic acid. So it's wrong. We need 2-methyl. And then over here, you don't have a dioic acid again because you end with serum 1O CH3, right? So it's a ketone over here on this side. So methyl ketone in fact. So basically D cannot be the answer either. So yeah, A is the answer. And then next question, 24. 1-chloro-1-methyl cyclohexane is hydrolyzed by heating with NaOH aqueous. The reaction pathway is shown. One carbon atom in 1-chloro-1-methyl cyclohexane is bonded to three other carbon atoms. What is the charge on this carbon atom at point C? Okay, point C. So if I look at this carbon here, which the chlorine is attached to, is this carbon is attached to three other carbon atoms. So basically, this is a tertiary haloalkane, right? Like the Cl is attached. The carbon that the Cl is attached to is attached to three others. So if it's tertiary, then it's going to react by SN1 mechanism, right? Which is a two-step mechanism, which because there's basically three electron releasing groups to this carbon, which means that a highly stable carbocation intermediate will be formed, right? And so basically this is nucleophilic substitution by SN1 mechanism, it's two-step and forms a stable carbocation intermediate, okay, because of the three R groups or alkyl groups. Okay, and looking at the reaction pathway diagram, this point is represented by the intermediate, and as I mentioned, it's a stable carbocation intermediate. It's a carbocation intermediate, which means it's cats are positive. It's going to be a positively charged intermediate, so it cannot be C or D, and it does not have a partially positive charge either. It's a stable carbocation intermediate. It's an intermediate. It's not a transition state. It's an intermediate, has a full charge, and so the answer is going to be B. Okay, so yeah, that is all. And then next question: malic acid is found in apples. Which reagent will react with only one of the OH groups in the malic acid molecule? So ethanoic acid in the presence of concentrated sulfuric acid. Well, ethanoic acid in the presence of it's in the presence of concentrated sulfuric acid. So it's not really like, I suppose this could be esterification. Yeah, esterification. So if it's esterification, ethanoic acid will not react with obviously carboxylic acid groups, but it will react with the OH group, right? So alcohol plus carboxylic acid will give you an ester, right? So, and it's in the presence of a catalyst, which is concentrated sulfuric acid, small amount of concentrated sulfuric acid. So esterification is going to take place, and it's not going to take place for these two, the OH groups of these two carboxylic acid groups, but this OH will definitely react. So I would say that the answer would just be A then, right? But let me check the other options. Sodium would react with all three of these, right? Sodium reacts with the OH groups as well as the CO2H groups. And why is it not erasing? And then sodium hydrogen carbonate would not react with OH, I believe, but it would react with the acid groups like CO2H and CO2H, right? So it would definitely react with those two. And then sodium hydroxide, again, the same thing. It would not react with OH, but it would react with CO2H and CO2H. Yes. We need a reaction with only one of the groups. So if this reacts with all three, this reacts with two of them, and this reacts with two of them, whereas this one reacts only with the OH, right? So that means that the answer is going to be A because that reacts with only one group. And then next question, which organic compound would not give either a yellow precipitate when treated with alkaline aqueous iodine or an orange precipitate when treated with 2,4-DNPH, dimethyl hydrogen reagent? Okay, so no orange precipitate means that no CO is present because no orange precipitate is gained. So if I see which of these compounds is either a ketone or an aldehyde, no carbonyl by the way. Okay, so propanal is an aldehyde, and so we can cancel this out because it's an aldehyde, right? Propanal, as the name suggests, aldehyde, propanal. So, and then propanone, as the name suggests, again, it's a ketone. So again, we're going to cancel it out because they said would not give either yellow precipitate or an orange precipitate. So the orange precipitate part means that because there's no orange precipitate, it has no carbonyl group. So we can already cancel out A and D. Now it's an option between B and C. Let me draw out B and C. So propane 1-ol, which is propane means it's a three carbon chain, and then 1-ol means that it has the OH group on the first carbon. Propane 2-ol means that it has OH group on the second carbon. Okay. Now, you're saying it does not give either. It does not give a yellow precipitate. So, yellow precipitate with alkaline aqueous iodine. That's the iodoform test, right? So, it's a test for either a methyl ketone, which is CH3, CO, basically, and something attached there. Or it's a test for secondary alcohol with adjacent methyl groups. It could be like CH3, C, um, H, OH, and then an R group here as well. Okay, so this is secondary alcohol because this is R group and this CH3 is attached to the carbon atom, which the OH is attached to, right? So over here we're talking about alcohol, so I guess we can eliminate this immediately. But does propane 1-ol have a second? Is propane 1-ol a secondary alcohol with an adjacent methyl group? No, it's not, because it has the OH group on the first carbon atom, right? So if it has the OH group on the first carbon atom, it doesn't really have CH3 branch. So we can immediately cross out propane 1-ol. But if you look at propane 2-ol, it's a secondary alcohol, right? Because this carbon atom is attached to two other carbon atoms, right? The carbon atom, the OH is attached to two other carbon atoms, so it's definitely a secondary alcohol, and is one of these adjacent groups. What do you call it? A methyl group? Yes, it is. In fact, both of them are methyl groups. So you do have a secondary alcohol with a methyl group that's adjacent to it, right? So this group, CH3, CHOH, and this R group, that means that it will give. Oh wait, they're asking about not, right? So this will give a positive iodoform test, right? Which means it will form a yellow precipitate with the alkaline aqueous iodine, right? Because it's a secondary alcohol with adjacent methyl group. So this cannot be the answer, because that about would not give either yellow precipitate or orange precipitate. So then the answer must be propane 1-ol, because it's not a secondary alcohol, it's actually a primary alcohol, right? Because this carbon atom that the OH is attached to is only directly attached to one other carbon atom directly. Okay, so it's a primary alcohol, and so it cannot give a positive iodoform test, so it will not give a yellow precipitate, and it's not a carbonyl either. It does not have C double bond O, so it cannot give a positive 2,4-D and pH test either. So the answer is simply going to be B. Okay. Next question. Question number 27. In which reaction is the organic compound oxidized? So we have CH3, CH2, CH2, CHO, which is an aldehyde, and it's reacting with Toland's reagent. Yes, Toland's reagent does give a positive test to the aldehyde. Aldehydes, like it's the silver mirror test, right? So you do it with ammonical silver nitrate, so AgNO3. That's what Toland's reagent is, and then AgNO3. There you have Ag plus, but then Ag plus gets reduced to Ag, which is Ag solid. So you get silver deposit, and that's why it's called the silver mirror test. And in turn, it oxidizes the aldehyde into carboxylic acid, so it becomes CH3, CH2, CH2, CO2H. Okay, LiLH4 is a reducing agent, so obviously it would not oxidize the aldehyde, right? It would reduce the aldehyde, in fact, to CH3, CH2, CH2, CH2OH, probably, yeah. Yeah, definitely. CH3, CH2, CH2, CH2OH, okay? So it would reduce it, not oxidize it. And then you have concentrated H3PO4. So concentrated H3PO4 with OH, I would assume it has a similar reaction to what the reaction of concentrated H2SO4 with alcohol is, under, the effect of heat. So basically, it would be a dehydration reaction or an elimination reaction to form an alkene, right? So you get CH3, CH double bond, CH2. I would assume that. So yeah, that's definitely not oxidation though. Okay, so I would cancel that as well. We've already got the answer as A, but we're just checking the other options. And then you have CH3COOC2H5 plus dilute H2SO4, which seems to be acid hydrolysis, right? Because you have dilute H2SO4 with an dilute acid. In fact, if you heat and reflux, then this ester will break down into carboxylic acid and the alcohol, right? So again, that's not oxidation, so we can cancel that out as well. And so the answer must be A. Next, how many of the following compounds produce a carboxylic acid on heating under reflux with an excess of hot acidified K2Cr2O7. So you need a carboxylic acid, okay? So if we oxidize this using K2Cr2O7, let me think about this. So you would get CH3, CH2, CO2H, right? Yeah, I mean, definitely. Why would it not be oxidized by K2CO2? If it's excess and hot and acidified, you would definitely get that. So, yeah, and this one is a ketone. A ketone cannot be oxidized further, can it? Like, let me just draw it out. So you have CO, CH, this is propanone, CH3. So how would that get further oxidized? Like, there's no way to get further oxidized. There's already a double bond with oxygen, and you have two adjacent groups. Carbon cannot form more bonds. Really, it cannot be oxidized, can it? There's no hydrogen to be replaced with oxygen, I guess would say. But yeah, it just basically can't be oxidized further. Ketones cannot be oxidized further. Then this one, CH3, CH2, CH2OH, it would be oxidized further. So it would be oxidized first to the aldehyde and then to CH3, CH2, because it's hot acidified, so I suppose maybe it will immediately be converted to CO2H perhaps. But yeah, CH3, CH2, CO2H. So that's method, propanoic acid. So then you have this one, which is CH3, CHOH, CH2. But then the thing is, I mean, this can be oxidized because this is a secondary alcohol, right? Like this carbon, which the OH is attached to, it's attached to two other carbon atoms directly. So it's a secondary alcohol. It can be oxidized, but the problem is that it will not be oxidized to a carboxylic acid. And that's what the question asks. The question wants carboxylic acid. See, again, this should be removed, and then you will get O. So this will be a ketone, which is propanone, basically, right? So it will be oxidized to a ketone, not to a carboxylic acid. So therefore, the answer, like the last one is not valid, basically. And since we only got first and so one, two, three, four, so we only got two of them that produce a carboxylic acid on heating and reflux with excess hot acidified K2Cr2O7, then that means the answer must be two of these compounds, which is basically option B. All right. Next, how many isomeric esters, including structural isomers and stereoisomers, can be made with the molecular formula C5H10O2 if methanoic acid is one of the two reactants used? Okay, so we already know that methanoic acid will definitely be the one of the reactants. So let me just say I will start the chain like this. Okay, well, so you have one carbon atom here, and for the methanoic acid, then we have O, which is a functional group COO, and then we have five in total, right? So one, two, three, four. Basically, what this means is that one carbon atom for the um, carboxylic acid, and then we have four carbon atoms for the alcohol part of the ester. Four C for the alcohol part, okay? So that's why I drew it like this. You could also draw it out in the displayed form, like this HCOO CH2 1 2 3. So let me just write it as CH2 thrice CH3, and you could draw it out this way. But skeleton is just quicker, faster, prettier, and more convenient. I mean, whoever invented skeleton formulas was amazing. Like, wow, this is like, I love skeletal formulas. Anyways, let's continue with the chemistry. Okay, so we have this, and so this is one of the isomers. Basically, I will just keep a tally in this place. Okay, so one of the isomers is this. Now I will keep the carboxylic acid part the same, but what I can do is I can make a branch. So it's 1 2 3, 1 2 3. I can make it like this, and then I can put a branch here. Okay, so this is one branch. So 1 2 3 4. It still has four carbon atoms. So that's another isomer. Then this one has no optical isomers or geometrical isomers. There are no stereoisomers basically, but this is a structural isomer. So because this one has this carbon atom has four different groups attached to it, but two of them are methyl groups. They're not four different groups attached. They're not four different groups attached, right? And again, for this one, it has two H atoms attached to it, so they're not four different groups. You cannot have optical isomers. And then we have we could have another isomer like this. So this could be another isomer, right? But then the thing is that here we could have optical isomers because this carbon atom, it has four different groups attached to it. I will show you. So this is one group, it's attached, and then the other one is this pink one that's attached, and some different colors. There's yellow one, and then there's also one H atom attached, right? Which you don't draw in the skeletal form, but it looks like ice cream a bit. Anyways, there's also an H atom attached. So it has one, like four different groups attached to it, right? So definitely it can have an optical isomer as well. So now we have one, two, three, four isomers possible, and then let's check if we can make further branches and stuff. I will see. We could make hmm, this compound. One, two, just keep it like that, and then we put two branches. Okay, so that could also be an option. And this one again would not have any optical isomers or geometrical isomers. No optical isomers because this carbon atom has three of the same groups attached, right? Like these three are all methyl groups. This is also a methyl group, this is also a methyl group, and this is also a methyl group, right? So it cannot have optical isomers, and obviously because it does not have a C-C double bond, so it cannot have geometrical isomers either, but this is another structural isomer, so that makes five in total. So one, two, three, four was the chiral center, and then five because there's no chiral center. Alright. So yeah. So in total, I mean I can't really think of any other ones, and the maximum option they gave is five. So I'll just choose five. Okay. So yeah, next question. Compound XC4H8O2 has an unbranched carbon chain. Okay. An aqueous solution of X has an approximate pH of 3. So it's probably a carboxylic acid then, isn't it? Because it has a low pH. And yeah, it has two carbon atoms, two oxygen atoms, sorry. And compound YC3H8O is a secondary alcohol. Okay, it is a secondary alcohol. So I can immediately draw out this compound X as well because this is an unbranched carbon chain, right? So I can say it's C. Let me just draw it like that. I love carbon skeletal formula because it is so convenient to draw. Okay, so I'm just drawing it skeletal. I'm lazy. Okay, so one, two, three, four. So it has four carbon atoms in an unbranched chain, just like this. Okay, compound YC3H8O is a secondary alcohol. So again, it's probably an alcohol. And there, even if you read the next part, X and Y are together in the presence of a little concentrated sulfuric acid. So definitely they're carrying out esterification, right? Because it's using sulfuric acid as a catalyst, a little amount, and to form Z as the major organic product. Okay, so we have that, and Y has three carbon atoms, and the only secondary alcohol you can form from that is propane 2O, right? So this is one compound, and this is the other compound, and now I have to find out what is Z. So let me draw out my compounds again. So this is X, and then I'm going to draw Y like this, okay, to make it easier to see the reaction that's taking place. These two are reacting together. So just sort of tilted it, okay, rotated it. Now you're upon esterification, you're going to lose water, okay, and so you will get this compound O and this, okay, O from here, and this, okay, so this is the compound, and they want the structural formula. So let me see what the structural formula will be. CH3, and then you have CH2, 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 then you have COO, and then you have C H, obviously because there's one H atom here that we don't draw in this chemical formula, and you have CH3 twice because there are two. You could write the two methyl groups like that. Okay. So now which one matches with what I got, and obviously you have water as well, right? But which one matches with what I got? CH3 twice CHCOO. So this part should actually be the carboxylic acid part, right? But you don't get the two methyl groups there, do you? So this is wrong. This doesn't match with what I got. And the second one, which is CH3, CH2, CH2, COO. Okay, that's right till now. And then CH, CH3. That exactly matches with what I got. So I would say that this is like B is basically Z. Option B is Z. Let's check the other one. This one is again wrong, but this one is right actually. CH3, CH2, CH2 twice, COO, and then this is a problem, right? Like you got CH2 twice, vertical CH2 twice, and I got CH3 twice, and CH. That's wrong. The alcohol part, and again, this one is the same as the same has the same problem as A, which is we put CH3 twice, CH with the acid, carboxylic acid part, but because it's CH3, CH3 twice, CHCOO, CH3 twice, right? So actually it should be CH3, CH2, CH2, COO, CH3 twice, right? So they basically got it wrong. So D is wrong as well, and so the answer is going to be B. Okay. Next question. In an experiment, 10 cubic centimeters of an organic compound J in the gaseous state was sparked with an excess of oxygen. Sparked. Okay. 20 cubic centimeters of carbon dioxide and 5 cubic centimeters of nitrogen were obtained among the products. All gas volumes were measured at the same temperature and pressure. Okay. What could be the identity of J? Okay. So what can we do? Okay, so let me just assume that this organic compound J, it has carbon, hydrogen, and nitrogen. Okay, so let me just take it as I will write it here, CXHY N Z. Okay, plus O2 because it's sparked with oxygen. They said, and I'm assuming that they used 1 mole of CXHY N Z. Okay, and then you're going to get carbon dioxide, oxygen, and nitrogen. No, you're just going to get, well, because it's a hydrocarbons. You're going to get carbon dioxide and water. When you spark it with oxygen and you combust it, and then you'll also get nitrogen, as they stated. So let me save this. Then because you have CX, like X atoms of carbon, so I'm going to take this as X moles of carbon dioxide, and then Y atoms of H. So over here you have H2O, right? So this will become Y by 2, H2O, because then you'll have Y by 2 into 2 is Y moles of Y atoms of H, and then N2 you have Z moles of N here, so I'm going to take it as Z by 2. Is it Z or Z? But anyways, Z by 2, N2. Okay, and then what's oxygen going to be? Oxygen from here you get x into 2, that's 2x, and from here you get y by 2, 2x plus y by 2. Okay, so oxygen is going to be 2x plus y by 2. You don't really need to find out oxygen, do you? I don't know, we'll see as the question goes on, but basically now I know that this organic compound has 10 cubic centimeters. So again, I am taking the ratio of, so basically if J is 10, and then I am taking, well, actually wait. So let me take the ratio of carbon to hydrogen, hmm, carbon to hydrogen to nitrogen. I mean, we don't know exactly hydrogen, but let's try. Okay, so we have carbon, they said 20 cubic centimeters of carbon dioxide. So if this is 20 cubic centimeters, X is 20 cubic centimeters, so that should give me the number of atoms of carbon in this compound. Then nitrogen was actually Z atoms, right? But over here we have 5 cubic centimeters of nitrogen. 5 cubic centimeters means that Z by 2 is 5, right? So Z by 2 equals to 5. So if Z by 2 equals to 5, that implies that Z equals to 10. Okay, so over here basically X is 20, Z, this is Y, and Z is 10, and we don't actually know what hydrogen is, so I'm just going to put a question mark. Okay. Then because this is like the organic compound J has like it's 10 cubic centimeters, right? So I am assuming that they used 1 mole to combust it, basically because I want to find the the number of atoms in this 1 mole, right? So I will just divide all of this by 10 because this is 10 cubic centimeters, so I'm just going to divide everything by 10. Okay, so if I divide it all by 10, this becomes 2 is to, I just keep it as a question mark, is to 1. I suppose that's why they give, like, if you think about it, I got 2 and 1, right? So over here I have C2, C2, and C2 N2. That is immediately wrong, obviously, because I got N as 1, right? So 1 is wrong. But that's why they give like H3 and H7, I suppose, because your H atoms, we don't really know how many there would be. So honestly, both of them could be valid. And obviously, if you eliminate option D, then because if you eliminate option 1, then from these options, C will have to be the correct answer. Because if 1 is wrong, then 2 and 3 must be right, right? So that's another way to think about it. That 1 is wrong, so immediately 2 and 3 must be right. C, but really it could be 3H2O or 7H2O, I suppose. Because oxygen, it can. We don't really know it. Depends on how much H2O is there as well. I mean, it depends on how much oxygen there is, how much H2O there is. It's excess of oxygen. The point, however, is that the answer could be 2 or 3, so the correct answer is C then. Okay. Anyways, next question. Three elements X, Y, and Z have electronic configurations as shown. Which formulae represent compounds that conduct electricity in the liquid state? Okay, so what is X26? I check my periodic table. So 2 6, right? So it is in group 6 then. So and in group 6, then it has two shells. So it's in the second period. So 1 2, and then group 6. So it's going to be oxygen, I think. So X is basically oxygen. Y is 2 at 1, so it's in period 3, and it has one electron in its valence shell, so it's going to be sodium. Then Z is also in period 3 because it has three shells, but it has 7 electrons in its valence shell, so it's going to be in group 7, so it's going to be chlorine then. So Cl. Okay, so I identified these elements. So now they're saying that conduct electricity in the liquid state. Well, probably that means there is an ionic compound. Maybe they're talking about ionic compounds. Because ionic compounds, they conduct electricity in the liquid state, right? Like not in the solid state, but then in the liquid state they have free moving ions, right? So they will conduct electricity. So then YZ will be NaCl. NaCl is definitely an ionic compound, right? One of the most well-known ionic compounds, I would say. So yeah, it will conduct electricity in the liquid state, and then Y2X will be Na2O, which is again an ionic compound, definitely, because metal, non-metal, and then again that's also metal, non-metal, so it will also conduct electricity in the liquid state. Z2X is Cl2O. Cl is a non-metal, O is a non-metal. That gives you a covalent compound, doesn't it? So that will not conduct electricity in the liquid state. It's a covalent compound. We're talking about ionic compounds here. So if 1 and 2 are right, that means that the option that's correct must be B. Okay, so the answer is going to be B. I don't know, my screen. Okay, nice. So next question, number 33. In this question, all gases can be assumed to behave ideally. Very nice. A chemist heats a mixture of nitrogen and oxygen gases in a sealed container at a constant temperature until the mixture reaches a dynamic equilibrium containing N2O2 and N2O2 and NO. The chemist repeats the experiment at the same temperature using the same initial amounts of N2 and O2, but at a much higher pressure. So, which statements about the second experiment at higher pressure are correct? At higher pressure, there are more particles per unit volume. Okay. At higher pressure, there are more particles per unit volume. So assuming it behaves ideally, right? So if you think about it using the equation PV equals nRT, particles per unit volume, that depends on the number of moles per unit volume. So N over V, and then we can shift the other stuff to the left-hand side to become P over RT equals N over V. So R and T are constant, right? This at the same temperature, and R is obviously ideal gas constant. But pressure, they increase the pressure, right? So if pressure increases, that means that this thing will also increase. N over V will increase. So according to the equation, and this RT is a constant, right? So if pressure increases, moles per unit volume will increase, which means particles per unit volume will also increase. So one must be right. And then second option is the composition of the equilibrium mixture does not change. So what do they mean by that? The composition of the equilibrium mixture does not change. So they mean the concentrations of each thing, I suppose. I guess that's right actually because it's the same temperature, right? But usually, it depends on the number of moles of gas on each side. But the thing here is that you have 2 moles on the left side and 2 moles on the right side. So if you increase or decrease the pressure, the equilibrium will not change. Like it will still, the equilibrium concentration will still remain the same because, you know, if you increase or decrease the pressure because they're the same number of moles on both sides. So increasing or decreasing the pressure will not change the equilibrium mixture. Okay, so that's right. And then third one is there are more collisions per second, so equilibrium is reached faster. That's definitely true because increasing the pressure, we know this from IGCSE that increasing the pressure increases the rate of the reaction, right? So, yeah, again, the frequency of collisions increases. There are more collisions per second, so equilibrium is reached faster, right? That's right. The frequency of effective collisions. Anyways, um, now frequency of collisions. An ethanol burner. Why am I just repeating random words? Okay, an ethanol burner can be used to heat water. If appropriate measurements are taken, a value for the enthalpy change of combustion of ethanol can be calculated. The equation heat transfer equals minus mc delta T is used as part of the calculation, which symbols are correctly described. Delta T is the change in temperature of the water. That's right. M is the mass of water used in an experiment. Mass of water is that's right. C is the specific heat capacity of ethanol. That's wrong, right? Because it's actually a specific heat capacity of water that we use in the equation. So if three is wrong, one and two are right. So the answer going to be it's going to be okay. So yeah, just remember that's actually the specific heat capacity of water. 35. The first ionization energies of 20 successive elements are in the periodic table are represented in a graph. The letters given are not the normal symbols for these elements. Which statements about this graph are correct? Elements B, J, and R are in group 18 of the periodic table. Well, let me see what this is B, this is J, these are definitely this seems to be true because they have the highest ionization energy and across a period, across a period, the ionization energy increases because the number of shells is remaining the same, right? So the shielding effect is fairly constant. But as I mentioned before, because the proton number increases, right? So the atomic radius decreases slightly because of that, because the nuclear force of attraction across the period will increase due to the increase in proton number. And since the nuclear force of attraction on the valence electrons increases, so that's why it will be harder to remove the outermost valence electron from the valence shell across the period, right? So that's why ionization energy increases across the period, which means that obviously at the end of the period you have group 8, right? So if you the highest ionization energy will definitely be for um group 18 or group 8. And then immediately after group 8, what happens when you go to the next period? A new shell is added, right? And since a new shell is added, there's a massive decrease. There's a massive decrease in the ionization energy because, there's an increase in shielding and an increase in atomic radius that's quite significant compared to, only a proton increase by only one, right? So whereas the increase in atomic radius and the increase in shielding is or the increase in the shielding effect is much greater. So that's why the ionization energy immediately decreases after group A to the next period. So next we have atoms of elements D and L contain 2 electrons in their outer shells. Okay, so if this is group 8, then obviously this is 1, 2, 3, 4, 5, 6, 7, and then this is again 8, and 1, 2, 3, what did I circle that? 4, 5, 6, 7, and then this is 8 again, and then this is 1, 2, right? So atoms of D and L, so where's D? D is here, so it's obviously it contains 2 electrons, means it's in group 2, right? So D is definitely in group 2, you can see from here. Then L is also in group 2, as I already labeled, so that means that 2 is also a correct statement. Then atoms of elements G and O contain a half-filled p subshell. Okay, so G, a half-filled p subshell. Let me see what G and O are first. So G is in group 5, okay, and O is also in group 5. So that does seem to be right. For example, if it's 2s2, 2p3, right? So that would be how it would be in its fifth shell. So 2 plus 3 means it has 5 electrons in valence electrons in total, but then 3 of them are in the p subshell because p subshell actually has uh, 3 orbitals, right? So and electrons never pair unless there are no empty orbitals left anymore, right? So after that you would have pairing, but if you have 3 electrons in the p orbital, as you can see from here, 2s2, 2p3, or if it's 3s2, 3p3, right? If because this is how it will be because it's in group 5, right? Uh, G is in group 5 and O is also in group 5, right? So if it has 2p3 or 3p3 or whatever, so then they will not be paired, they will be unpaired. One here, two, a second one here, third one here, and then you have space for 3 more electrons, which means that it is a half filled p subshell, right? It has 3 electrons, 3 more can be added, so it's half filled p subshell. So all 3 of them are right, so the answer is going to be A. Okay. Now, question 36. Which properties increase in the sequence hydrogen chloride, hydrogen bromide, and hydrogen iodide? So let me just write down HCl, HBr, HI. Okay, so down the group basically in that sequence. And so thermal stability, bond length, ease of oxidation. Okay, so down the group, use chlorine perhaps is this size, then bromine is bigger than that, iodine is bigger than that. So, and H obviously remains the same size throughout. So then basically because the halogen atom is increasing in size from Cl to Br to I, right? That means that the bond length here will increase, right? There's a greater distance between there will be a greater distance between the nuclei of the halogen and H. So if the bond length increases, then the bond is weaker, right? Bond length is inversely proportional to bond strength. So if bond length increases, then the bond is weaker. So again, wait. So which properties increase this, right? So as I've already mentioned, bond length increases, and the bond length increases. So bond strength is less, which means bond. Obviously, bond strength is the same as bond enthalpy. So bond enthalpy is less, which means that it's easier to break bond because it's a weaker bond, so it's easier to break it. So Hi is broken the most easily. Um, and because of that, thermal stability of Hi is the least because it's the easiest to break because it's the weakest bond, right? It's broken the most easily. It has the weakest bond strength, least bond strength. So it's the thermal stability basically. Well, actually, they said increase. It's not with that. So again, thermal stability decreases. Basically, Hi will decompose much more easily than HCl, right? So a lower temperature is required to break down Hi. It will break down at a lower temperature, so it's less thermally stable than HCl basically. Thermal stability decreases. Ease of oxidation, on the other hand, um, ease of oxidation. Ease of oxidation should increase actually because again the bond strength has decreased, right? So the bond is weaker, like Hi bond is weaker, so it will be oxidized more easily by using, for example, any oxidizing agent really, like H2SO4. So yeah, I mean H2 4 SO4 is an acid, but then with HI it would oxidize HI and it would oxidize HBr, but then with HCl it would only act as a acid, I suppose. So yeah, and yeah, so ease of oxidation also increases like HI is because of a weaker bond, so it's easier to oxidize. Okay, and then the diagram shows a compound used as a flame retardant. Which statements about this structure are correct? Okay. The empirical formula is C2H3Br. Okay, let's see. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbon atoms with C12. How many H atoms are there? The areas is all. So there's one H atom here. So H, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 11, 12, 13, 14, 15, 16, 17, and 18. So it's 18. And how many bromine atoms are there? It's so weird. Okay, anyways, 1, 2, 3, 4, 5, 6. Okay, so there we are 6. Now we can, all of these come in the 6 times table, right? So we can divide them by 6. So we get C2H3Br. Is that the same thing? Yeah, it's the same thing. So this is right. The C12 ring is not planar. That is also right. I'll tell you why it's right. It's because each carbon atom here is forming 4 single bonds, right? Like for example, this carbon atom that I have, let me highlight it actually. Highlight it. Okay, so I've highlighted it. Then it has one Br attached to it. Then, if I just draw a line here, so this group is attached to it, sort of, and this group is attached to it, and there's also one H atom attached. So it has 4 groups attached to it, right, with single bonds. 1, 2, 3, 4. So 4 single bonds. So since it has 4 single bonds, it has a steric number of 4. It's carbon that I've highlighted, and no lone pairs. So that means that the bond angle is 109.5 degrees, right? So it's basically a tetrahedral shape. And let me illustrate one tetrahedral molecule, for example, CH4, okay? So this is how CH4 looks like, kind of. So here the bond angle is 109.5 degrees. This bond angle, for example, or any bond angle, any HCH bond angle. And, we represent this using dotted lines and wedges because to represent that the bonds are not all in the same plane, right? Whereas, in the previous question, we talked about trigonal planar, which means, it lies flat on a paper, basically. All the atoms are in the same plane, whereas it's not the case in tetrahedral molecules. That's not the case in tetrahedral molecules. And as I showed you, this blue atom, carbon atom, is forming 109.5 degree bond angle, and basically, um, you know, it shows that not all the bonds lie in the same plane, because of the tetrahedral geometry here, and with all the other carbon atoms as well. So because of that, not all the carbon atoms lie in the same plane, and so the C12 ring is not planar. So that's basically the logic. Like maybe this is towards this part of the ring is towards you, and this is away from you and stuff. So the carbon 12 ring is not planar basically. Okay, and then there are 6 chiral carbon atoms. Again, as I like, even if I take this example of again this one that I've highlighted blue, so and this I drew this line of symmetry earlier, so there actually is no symmetry, right? Like if you see this part of the molecule, like there's a Br here, but there's no Br here. There's a Br here and a Br here. Okay, but then there's a Br here and no Br here, and there's a Br here. Like it's not a symmetrical molecule basically. And if you check, and it has one group attached here, H, and then one Br attached here, this carbon atom that I've highlighted, and then this one group attached here that's not symmetrical to this group. There's no plane of symmetry, which means this is a chiral carbon atom that I've highlighted in blue. Similarly, if you check the other carbon atoms, this one has no plane of symmetry either in the molecule, so this is also, I highlighted too much, man. But this is also a chiral carbon atom. Okay, this is also a chiral carbon atom. There's no plane of symmetry. Yeah, there's no plane of symmetry. You see this Br? There's no Br here. Okay, and then this one is also a chiral carbon atom because there's no plane of symmetry, and then this one is also a chiral carbon atom. This one also chiral carbon atom. We have 6 Br molecules, and so we have 6 chiral carbon atoms. The other ones which don't have a Br attached, they actually have 2 H atoms attached, right? So H atoms are obviously identical, so that means that this one cannot show chirality because this carbon, the ones in I'll highlight in yellow now, so these ones cannot show chirality because they have 2 identical H atoms attached, right? And because of that, it cannot show chirality because for chirality you need, a chiral carbon is required which has 4 different groups attached to it. Different. So basically 1, 2, 3, 4, 5, 6. It has 6 chiral carbon atoms, and since all 3 of the options are correct, it's going to be A. Okay. Next we have one of the active ingredients in tea tree oil is terpene-4-ol. In the diagram of the skeletal formula of terpene-4-ol, 3 of the carbon atoms are labeled 1, 2, and 3. Which of the labeled atoms are chiral? Okay, so again for chiral chirality or chiral carbon atoms, you need um, four different groups attached to the carbon, right? And four different groups attached means it has to have four single bonds, right? Or four sigma bonds, basically. So it cannot have any the carbon atom cannot have any double bonds with it, okay? So over here, 2 is immediately wrong because there's this double bond, which means that, it's attached to this same group, sort of, twice you could say, or, there are not four different groups attached. So 2 is immediately wrong. 1 is right because, let me just check if 1 is right. I mean, I just said it, but check it properly. Is the molecule symmetrical? No, it's not. Because here you have a double bond, you don't have a double bond on this side or anything like that. I mean, obviously you don't, because otherwise the carbon would be 1, 2, 3, 4, 5. It could have 5 bonds. That's obviously not possible. This is not a symmetrical molecule about this line of symmetry that I've drawn. There's this group attached, and then this group attached, and then that group attached, this group attached. There are 4 different groups attached to this carbon atom, which is labeled 1, so that's definitely a chiral carbon atom. And 3, on the other hand, is not a chiral carbon atom. Why? Because 3 has one H attached to it, that's right, and then this whole group attached to it. But it has 2 identical methyl groups attached. Oh, too much highlighting. Wow, okay, whatever. But basically, it has 2 identical methyl groups attached here, like 1 and 2, right? So if they're identical, then it cannot be chiral, right? So it's only 1, which means the answer is going to be D. Okay, because 1 is the only one that's chiral. Number 1. Okay. Next, propanal reacts with hydrogen cyanide to form 2-hydroxybutane nitrile. A suitable catalyst for this reaction is sodium cyanide. Right. Which statements about the reaction of propanal with hydrogen cyanide are correct? Sodium cyanide provides a stronger nucleophile than HCN. That's right, because HCN is a weak acid, right? It only partially ionizes in aqueous solution. So it's like H plus Cn minus. So the concentration of Cn minus ions is not very high with HCN, right? But whereas in NaCN, the thing is that NaCN, Na and Cn have a much greater electronegativity difference, right? Like Na plus is more electropositive, or you could say that. So there's a much greater electronegativity difference between Na and Cn compared to H and Cn. So because of that, Cn minus is formed more easily or in greater amount, I guess you would say. But so because of that, you will get, NaCN is a stronger nucleophile than HCN because more Cn minus is formed with a greater electronegativity difference, I suppose. I mean, at least that's how I think of it. If there are better explanations, you could write it in the comments. The reaction can be classified as nucleophilic substitution. That's wrong, because this is a aldehyde reaction, right? Like, carbonyls like aldehyde and ketone, they react. Their what do you call it? What do you call it? Like, characteristic, I suppose, mechanism is nucleophilic addition, right? So it should actually be nucleophilic addition. So that's wrong. Since 2 is wrong, 3 must be wrong as well. So the option is D, but answer is D. So, but let me read the third one as well. The hydrogen cyanide molecule attacks the propanal molecule to form an intermediate ion. Yeah, that's right. I mean, what do you get? You get CH3, CH2, COH, and this is partially reagent. Try that. I should get some more space. Let me erase this. CH3, CH2, CO, CHO, and then this is partially negative, and this is partially positive. And what's going to happen is you have the Cn molecule here, it's Cn minus, and then this is going to travel here, and then that's going to go there, and then you're going to get basically they said the hydrogen cyanide molecule attacks the propanol molecules, propanol molecules. So what's happened, and then do you get an intermediate ion? Yes, you do. Now I don't really have space, but I will draw it. So you have a negative charge on that because you don't care, and then you already have an H there, and the Cn gets attached. So as you can see, this is an intermediate ion. Um, yeah, and so you do get an intermediate ion. Then you could, of course, continue the mechanism if you want. So you have this going like that, and then this is partially positive, partially negative. That's why it happens. And then this O just attacks this H, and then we have CH2, CH3, CH2, CH, OH, CN plus Cl plus Cn minus again. So basically, yeah, this mentioned that NaCN is a catalyst, right? So this one will, sort of NaCN, and that also we can say comes from the NaCN. So, or ACN, but yeah, basically the Cn minus has been regenerated. So that's why they mentioned that a suitable catalyst for this reaction. So it's acting as a catalyst, right? So yeah, you do get an intermediate by the HCN molecule attacking the propanal molecule. So three. Wait a second. This is the hydrogen cyanide molecule. Yeah, it's wrong, right? Because I I just mentioned it right now and I still said it. Okay, but basically this Na plus is being regenerated, right? Like Na plus Cn minus. No, Na plus Cn minus and then Na plus Cn minus is being regenerated here. So it's actually the not the hydrogen cyanide molecule that's attacking the propanol molecule. Is actually this just the cyanide ion from NaCN. You got it from Na plus Cn minus. So yeah, that just shows that you should read questions carefully, which I don't always do. And yeah, so it's NaCN that attacks it, and then well, actually Cn minus from NaCN, and then it gets regenerated at the end. So over here you have NaCN, and then here you have NaCN, which is why they mentioned that it acts as a catalyst. So funny how sometimes people say stuff and then they forget that they said something and they say the wrong thing. I don't know. I just did that right now. Anyways, whatever. Which syntheses will be successful? Okay. CH3, CH2, CH3 from CH3, CH double bond, CH2 plus LiAlH4. Um, well, no, it will not be successful because alkenes, it's not an alkene. Alkenes cannot be reduced by LiAlH4. I mean, alkenes can be reduced by hydrogen gas in the presence of nickel catalyst at high temperature, and pressure like 150 degrees Celsius to 200 degrees Celsius, but they cannot be reduced by LiAlH4 in dry ether. So one will not be successful. Two, CH3CHOH CH3 from CH3COCH3 plus NaBH4. Wait, so this is CH3COCH3, okay. And NaBH4 can reduce ketones. Yes, it can. That will give you OH. Is it the same thing? CH3CHOH. Yeah, it's the same thing. This is possible, definitely. So 2 is right. So what about 3? So you have CH3, CH2, CHO, which is this thing. And you want to reduce it using NaBH4. Can NaBH4 reduce an aldehyde? Yes, it can. It cannot reduce carboxylic acids though, because it's a weak reducing agent. But it can reduce aldehydes or ketones, and so this will become this thing, which is CH3 is matching CH3, CH2, CH2, OH. Yes, that matches with what they wrote in the question. So that means that 2 and 3 are right, which means that since 1 is wrong and 2 and 3 are right, which option is that? C. Okay, so the answer is C. So yeah, the paper is done, and some questions were a bit tough in this paper, I guess, and I said some things wrong, which I corrected later. But maybe if I missed anything or if I did say anything that's wrong, please do correct me in the comments. But thank you so much for watching. If you have any specific um, videos you want to see me upload, then you can tell me. And thank you.